Welcome back. So we were looking at this theorem. Let S be the set of vectors v1 through vn, set of n vectors in Rn. R super n stands for columns, R sub n stands for rows. Let A be the matrix whose columns or the rows are elements of S. Then S is linearly independent if and only if determinant A is non-zero. Let's look at the proof. We prove this theorem for column vectors, as the proof for row vectors is similar. How is this similar? If you remember, determinant of a matrix is equal to the determinant of its transpose. So if you are working with rows, all you do is take its transpose and check its determinant. The rest of the argument is identical. Now, we want to check whether this is linearly independent or not. So consider a linear combination of these vectors equals the zero vector. To solve for scalars a1 through an, that is the coefficients a1 through an, that should be an n. Consider the augmented matrix A, right hand side is the zero vector, where A in turn is just the columns v1 through vn. A is an n by n matrix. Why? Because each vector is of size n and there are n vectors. So n size n by n matrix. Further, we know that the coefficients are 0 is the only solution if this A can be inverted, right? This is an old result we saw from chapter 3. All right. There is a solution to this system, linear system, if and only if A is invertible. What does invertible matrix look like? Its determinant has to be non-zero. So it's all an if and only if statement. So that is straightforward. Your vectors are linearly independent if and only if the matrix found by these vectors is invertible, which in turn means the matrix has non-zero determinant. Now let's consider the next theorem. Let S1 and S2 be finite subsets of a vector space. Suppose S1 is contained in S2. Then the following statements are true. If S1 is linearly dependent, then so is S2. That means if the smaller set is linearly dependent, then so is the bigger one. On the flip side, if the bigger one is independent, then so is the smaller one. This is an important theorem, everyone. Suppose S1, the smaller set is V1 through Vk. S2 is a bigger set that contains S1. So not only does it contain V1 through Vk, it contains somebody else, W1 through Wm. So it contains a few more elements. So let's look at the first one. If S1 is linearly dependent, then there are scalars dependent. There are scalars A1 through Ak, not all 0, such that the linear combination is 0. That's the definition of being dependent. You may find scalars not all 0 such that the linear combination is the 0 vector. Which means I can use the same coefficients A1 through Ak for V1 through Vk and then 0 for the Ws. So notice I still have some non-zero coefficients resulting in the 0 vector. Okay, all I placed was zeros for here so that I don't change my previous equation. In other words, I have found a linear combination of the bigger set with some non-zero coefficients resulting in the 0 vector. All right. Therefore, the bigger set has to be linearly dependent because we found some coefficients which were non-zero. Okay. On the other hand, so that completes part 1. Let's look at part 2. The bigger set, suppose it is linearly independent. What does that mean? Take any linear combination of the bigger set resulting in 0 then the coefficients have to be 0. That's the only possible solution. We want to show that S1 is linearly independent. Suppose we have a linear combination of the smaller set V1 through Vk. For some real numbers, linear combination is the 0 vector. Well, the same trick we played earlier. Extend that equation by putting in zeros for w's. Now you have a linear combination of the bigger set equals 0. But you see, we have assumed that bigger set is linearly independent. That is, a combination can give you 0 if the coefficients are 0. That's the only possible solution. Okay? So all the coefficients have to be 0, not just these, even the a's have to be 0. So we started basically with a linear combination of the smaller set and found out all the coefficients had to be 0. So the smaller set has to be linearly independent. Okay, this should be S1 here. Smaller set is S1. Here is a consequence, important consequence. We know that the set containing 0 vector is linearly dependent. Why? Take any non-zero number, scalar multiplied to 0. Well, any number scalar multiplied to the 0 vector is a 0 vector. So even if you have somebody non-zero, it's a 0 vector result, which means the 0 vector by itself is linearly dependent. From the theorem we just proved, if you have a dependent set, then anything bigger than that will be dependent. So any set that contains the 0 vector is linearly dependent. Now, on the other hand, suppose you have a set containing only one non-zero vector. Then that set has to be linearly independent. Why? Suppose S equals the set containing one vector where that vector is non-zero. Suppose a scalar times the vector is the 0 vector. Then we have seen by theorem, by one of the theorems in section, I believe 4.2, we have seen that this is 0 vector, then the scalar has to be 0 or the vector has to be 0. But our assumption is the vector is non-zero. So the scalar has to be 0. What does that mean? A linear combination of this vector equals 0 vector means the coefficient is 0. That is, that set is linearly independent. A collection of vectors where a vector is repeated is linearly dependent. So notice I'm saying collection. Okay. Technically, a set is a collection where elements are not repeated. So I cannot call this a set of vectors. I'm calling it a collection of vectors where some vector is repeated. If you repeat a vector, then it's automatically linearly dependent. Why? Suppose you have a collection V1 through Vk. So notice I've used bracket instead of braces. Suppose you have a collection V1 through Vk where the first two vectors are equal. Then 1 times the first vector plus -1 times the second vector and 0 everywhere else. 1 V1, -1 V1, you see V1 and V2 are equal. They will get you the 0 vector. So you found a linear combination with some non-zero coefficients to result in the 0 vector. That is, the collection is linearly dependent. Suppose a set of two vectors is linearly independent, that is V1 and V2. No, that should be dependent. Suppose you have a set of two vectors which is linearly dependent, then there exist two real numbers a1, a2 not both 0 such that a1 v1 plus a2 v2 is 0 vector. One of them has to be non-zero because they are dependent. Suppose a1 is non-zero. Divide both sides by a1. You are able to solve for v1. v1 is -a2 over a1 v1. You see, this should be V1 and this should be V2. Okay? V1 is dependent on V2. V1 is a scalar multiple of V2. Hence the name dependent. You can solve for one vector in terms of the other. So please make this note. This is V2. The point is, if A1 is non-zero, I can divide this equation by A1 and solve for V1. That is, V1 is dependent on V2, hence the terminology dependent. Okay? So here is an important theorem. The non-zero vectors, you are taking V1 through Vn in a vector space V, are linearly dependent if and only one of the vectors, some vector starting from 2 onwards, is a linear combination of the preceding vectors. So starting from 2 onwards, there is some vector Vj which is dependent on the previous ones. Okay? We will prove this in our next video because this is a detailed long proof.